Hi everyone and welcome to a new video. In this video we will discuss the performance indices used in controller system design, and this is a very important topic where you want to have an optimum design of your system. So let's look at our outline first before we move on the actual discussion. In this video we have the following topics. We have the design criteria, so I will first discuss what are the design criteria, like the delay time, the rise time due to step input, and also the peak time, the settling time, which can be due to the step input, also an overshoot, and also the steady state errors, which you can have due to step, ramp, or acceleration inputs. In addition, we will also discuss the performance index or indices, so different index, and also the quadratic performance indices, and also specifically the optimal for the optimal system, and also discuss the spectral factorization theorem, and also the optimal overall transfer function. Now we will then give an example, numerical, to discuss the situation in more detail and determine there an optimal overall transfer function. Now also discuss how to compute a spectral factorization using hand calculation also in MATLAB, and then do that also using an example. Now the fourth topic is the selection of the weighting factor, which is what we will use when we have a performance index. Again, we will give an example here, the third example, how you select such a weighting factor in specifically a third order system. Then we will move on. One of the performance indices that is used most often, ITAE optimal systems. Now we will look at three specific errors, and when we talk about the zero position error optimal systems, and give an example about that specifically for second order system, and also the zero velocity error optimal systems, and also discuss an example there. And finally, we also look at the zero acceleration error optimal systems. So this is the outline for this video, and I hope it will clarify the situation for you in great detail. So let's look at the first topic, which is the design criteria. Now, from a transient response specifications that are dependent on initial conditions, of course, of the system. So a practical system often exhibits damped oscillations before reaching a steady state condition or steady state region. So we have a system in general, we have an input, and we have an output given here in Laplace parameters. It could be that you have such a response, and we see a lot of details here. So let's go through them one by one. What we see is the following from this transient response. This is a unit step response, which is called the input is a unit. So that is actually this black line. So that goes from 0 to 1. And then the response is that this undamped response also in black given. Now we see several things here. So if we have the delay time due to step input, that is actually this time, which is actually the time to reach 50% of the, let's say, the steady state value of your output. The rise time, we also see that is actually shown here. So the rise time. We also see the peak time, to the time actually the first maximum peak is reached, and also the settling time due to step input, or it could be, of course, ramp or acceleration. We have also the overshoot, which is how much you deviate from your steady state value in percentage or as a factor. We have also the steady state error, so how much you deviate from the actual command input signal. So let's then clarify this again, and then the delay time. It is the required time to reach 50% of the final value, as said before, for the first time. And for rise time, it is actually the required time to raise or rise that output value from 10% to 90%. That is one of the criteria. It could be that you have it from 5% of 95 or from 0 to 100% of the final value. We see here that is actually the third one which is used. So from 0 to 100%. Now for undamped systems, second order, this is most often used. So that's actually why you also see this here, the TR. But for overdamped systems, or where you don't have this overshoot, most of the time it is used between 10% and 90%. So it really depends on how your response is looking. The peak time is the required time to reach the first peak of that response. So the first peak here, that's the TP. The settling time, in this case, we look at a allowable region or tolerance. It could be 2%, 0.02, or 0.05 or 5%, or it could be even 1%, 0.01. So it really depends on your criteria and how strict you are. So required time to reach and stay within a given range. Now the overshoot itself is defined by this. So the MP is defined as the maximum value of that output minus that state value over the steady state value, which is times 100%, could be a percentage, but this is given as a scalar value. The steady state error is how much difference you have in your final value between input and output amplitude. So if I look at this output, it really reaches that 1. So in this case, the steady state error is 0, but it could be that it is lower or higher, and that is an error due to that command window, or command input 1. Okay. Now let's then look at the performance indices, because why do we need that? Now let's make a simple comparison between two systems we have designed. So we have designed according to the specifications that the G1 and G2 are produced. So G1 has a good transient response, but not that good, really poor, actually poor steady state performance. This is the G1, so it has a nice transient, so there is not much an overshoot. It is quite fast, but from a unit step input I only reach 0.5, so my steady state error is quite high, 0.5. So I reach actually 0.5, but I must go to 1. So that is definitely a very poor steady state performance. Now this G2 has a very poor transient response, but quite good steady state performance, and this is this. So you can see that it's quite high overshoot, again unit step response, but it reaches the steady state value you want. So it's actually reaching that 1. But overshoot is 110% approximately, so definitely not what you want. So which of these two systems should we use? So which one? That's actually the problem of selection and also the performance indices. So the performance indices or performance index is a quantitative measure of the performance of your system. And it's selected such that the importance is given to a specific system specification. So if, for example, the rise time is very important and not that much the overshoot, then this system is preferred because it rises much faster than this one. But if the overshoot is much important than the other parameters, then this is definitely not the best solution. But if everything is a little bit important, then of course we need to have a much more solid analytical index for that. And that is really the topic what we see next. So how can we then make that a little bit more accurate? Now let's modify our criteria in this format. So we can say there is the index, which is called J. It is some constant K1 times delay time. So that delay time is multiplied by some K1 constant. Same for the rise time. For the peak time, it's its own constant. And also the settling time, overshoot, and the steady state error. So we have 6 specifications, each of them multiplied by its own constant, K1 up to K6. And this is now given in a formula form. So where K1 up to K6 are the weighting factors. So it is a weighting or a scaling of how much importance you want to put on these specifications. Now the weighting factors are chosen according to the relative importance of the specifications. For example, arise time, overshoot, settling time, etc. Now having a system with the smallest index j is called optimal system with respect to the criterion j. So you would like to minimize, that's actually sort of the optimization problem, this number j. Okay, given of course the K1 up to K6 for these specifications. However, this is not that easy to determine analytically, and it could be also really lengthy process. So for this optimal solutions, we have a very difficult process and difficult to trace the criteria. So more traceable criteria we would like to use is actually given here in general form. So this is a very general feedback control system. We have our plant and there is a controller in cascade. And this is now shown here in a feedback configuration where you measure the output using an output transducer. We give it here to a summation point, and also you command here at the input via an input transducer. So you transform your input signal. Let's say you apply some current here that will be then converted voltage via this transducer, and then you compare these two signals, and that will produce an error which is the actuating signal to actuate your controller. Now if you make it a little bit easier, so you actually say, okay, the transducer for the input and output and also the controller, I just forget about that and only focus on the plant and also the output and input. Then you have this more simplified diagram. Your actuating signal, again, the input and output, and also the plant specifically, so only the plant. Now, the error in a unity gain feedback configuration here is given by the AE is equal to R minus Y. And if you now do the inverse Laplace transform, you will get then the time domain representation of the error, your actuating signal. Now, the traceable criteria is actually saying the following. Now, if the error is present every time, we should consider also the total error, not just at some specific time or time slot. That means you need to, for example, look at the graph. The green one is the input and the blue one is the response. And if you look at the red one, which is the error for each time, you might think, okay, let's then look at a total error. What is total error? We think directly in calculus about integration. So let's then integrate total error. So let's call this another performance index J1. So we will integrate from 0 up to infinity of that error. However, this is not really useful index because this part, the area here, is positive and this part is negative. This part is positive, so you will have partially cancellation of the errors, which is not what we actually interested in. We are interested in a total error, not the cancellation of the errors. So it is okay, but due to that cancellation, it doesn't represent the actual error. Now, what is then better criteria? Now, you can also say, let's then look at the integral of the absolute error, which is then short here for IAE. And that is then J2, which is then similar to that one, but then the absolute value of the error. If also the integral of the squared of the error, which is then given by this different index. Now this part is also plotted here. We can see that. So just the square of the error. And if you now also want to have the total error of that one, you integrate this and you will get the J3. So really depend on what you think it is more important. Okay, now you can also do the following, the integral of the time multiplied by the absolute error. So different, and this is actually most often used, and we will see that in the later discussion. And that's in J4. So actually you have a time times the absolute value of your error, and you will integrate that quantity. Again, from 0 to infinity. Okay. Now, if I look at these two specifically, ISE give actually more attention or penalize more the large errors more heavily than the small errors. Why? Because it is actually at the beginning, you can see that, it integrates much heavily than the small errors. This one, the fourth one, J4, so ITAE, doesn't put too much weight on large errors at small t. This is in some sense better and also more realistic because you have a lot of transient effects at the beginning. So that's also one of the reasons to use this instead of this. Okay. So is this enough? Now, if we consider physical systems, we have also physical constraints like available power, maximal rotation speed, and also other parameters like how much you can compress or extend your spring. Really physical limitations we have. So the actuation signal or your error must be then also limited because you cannot just put in a lot of energy in your system because the math says so. So we really need to check also how far we can go. So you have some actuating signal U that must be smaller than or equal to some constant A for all time, and A is a constant. Now the conclusion, in order to use the performance indices up to now we have discussed, you should also consider the physical limitations. So don't forget that. So just mentioning these indices without any actuating signal limitation, it is not enough. It doesn't say anything. Okay. Now let's go to the next topic, which is about the quadratic performance indices. Now we have an optimal system. So how to design an optimal overall system to minimize the quadratic performance index. Again, our diagram of a unity gain feedback with our input, output, and the error. Error given by this in the Laplace domain, and in the time domain it is given by this expression. So if I look at ISE, again integration of the square of that error, you will have this expression. So we have the r minus y squared quantity. Now let's call this equation number 1. Now it must be subject to some constraint, which is then for the actuating signal, which is then smaller than or equal to some A for all time, for time larger or equal to 0. And A again is a constant. Now we have some difficulties again using this integration because there is no simple analytical method available to design such a system. Is there really again a limitation we have in analysis? An optimal system may be nonlinear or even not time invariant. So it can be time variant, and that will be of course more complex. So in order to make life a little bit easy for us, we can also say if we limit our design to linear time invariant systems, so LTI systems, then one must be replaced by another performance index. So instead of ISE, we can also replace it in this form. So we can say, okay, let's give a difference between the R and the Y, so the reference input and the output. Let's give that, of course, squared, give that a weighting factor Q, and also add to that the U as the actuating signal. So this instead of this, equation number 1. And then call that equation number 2. Now, Q is a weighting factor, it must be larger than 0, so it's positive. Now, if Q is very large, then there is more emphasis, more weight place on the error. So then this part is much larger than the u squared. But if q is, let's say in the extreme case, infinite, then ut can be ignored because this part is almost nothing compared to that one. Then your integration actually is only determined by the first part of your integrand. And you can also say, let's then use just this without that u. But if you take the q as 0, so you actually make this 0, then the performance index j here will then simplify to integration from 0 to infinity of the u squared. So we have now two extremes. One of them is infinite, the other one is exactly 0 for the q. Now let's call this equation number 3. What happens? Thus the optimal system in this case that minimizes the criterion is when the u is 0. That is sort of logical because we want to have also the actuating or the error 0. And that's what you get when you don't put too much weight on that error. Okay. Now let's bring then again the important parts together and move on. We have now two extremes as discussed. One of them is the q goes to infinity. We get this. The other one, if q is 0, you will get this. Okay, the conclusion is then the following. Formally, we should use equation number 1, where you see the r and the y as a the difference squared. Now, if q is properly chosen, then the constraint, what you have here, for a u actuating signal smaller than or equal to a for all time, will be satisfied. And also we can replace equation number 1 by equation number 2, which is then actually this. If, of course, these condition is met, so that if q is chosen properly. Okay, so that's actually also one of the changes we need to make in order to calculate this more easily analytically. Now, if I now consider, for example, a plant which is given in general form by this, so the numerator divided by the denominator, so g is equal to n over d. Now, assuming that n and d has no common factors, so there is no pole zero cancellations, and the degree of n is equal to or smaller than the degree of d. So if n is, let's say, is degree of 2, then d must be at least 2 or higher. Now let's see a design problem then. What is the design problem? Find an overall transfer function that to minimize that quadratic performance index, which is this. Again, our index we will use, which is then more easily than the formally one. The next topic is the spectral factorization. This is important theorem to continue our analysis. It says the following. Now we consider a polynomial q which has the ds times the d minus s plus that q again times the numerator s times the numerator with a minus s included. So q is formed by the numerator and the denominator of the plant. We have here given in a general form, and also the weighting factor. Okay. Q is, by the way, equal to minus, Qs is equal to Q of minus S. Thus, if you have, for example, pole S1 for this Qs, you will also have a minus S1, so another pole which is at the opposite side, also for the same polynomial. Now, Q has no poles on the imaginary axis. That is also mandatory. And you can also see the diagram here. So if the pole here is here, there is one pole. The other one is minus, so it will be then here. And the other one will be here, and the other one will be here. Or it will be on the real axis, but it will be never on the imaginary axis. So we need we denote the left-hand plane poles by D0 or DO as we know the right-hand pole, so all of them in the right hand, we call that DO minus S. This DO polynomial is also called the Hurwitz polynomial. Then we can write the QS as follows. So we can say ds times d minus s plus the q times ns times n minus s will be then dos times do minus s. And this is a very important equation we will use. We won't derive this, we will not prove this is true, we will use it for our discussion. And this is the spectral factorization. Okay, the optimal transfer function. Now, it is implementable overall transfer function, GO, to minimize the quadratic performance index. And this is the index, again, that we will use. The Q, again, is a weighting factor and also our actuating signal and also our error here. Now, if the Q is larger than 0, because that is mandatory, and for example, the input, the reference input is a step input, so then this is in time domain just 1 for all t equal to or larger than 0. Now, if I now consider the spectral factorization, I can write this, as discussed before. And again, this is the Hurwitz polynomial. Then the optimal overall transfer function, is then given by this one. So this optimal overall transfer function has this formula. Again, what we want is a Q, which is our weighting factor. We have our numerator for the plant evaluated at S0 and also the numerator of the plant itself, divided by the polynomial here we have determined, or we will determine, using this spectral factorization, and also evaluated at 0. And also what we have in the denominator is the same spectral factorization polynomial. So this is the formula we will use. Again, we will not write this, we will not prove it. It is what we will use. Okay, now let's go through an example and then determine an optimal transfer function for this plant. So we have a plant given by 1 over s times s plus 2. So it is a second order system with a pole at the origin, also pole at the minus 2. So it's already stable in this format. So we would like to have an optimal overall transfer function, so G optimum, to minimize the following performance index, which is then given by this, when the input R is a unit step reference, and also the weighting factor Q is chosen as 9. So we just selected some number. Let's see if that really works out perfectly. So let's look at the solution. The Q, we start with the Q, set up the Q, so we have the D and D of minus S, etc. So we see that N is equal to 1, and the D is equal to S times S plus 2. Okay. Now if I do N of minus S is still 1, and the other one, D of minus S, will be then minus S times minus S plus 2. Okay, now then we get the following. We just work this out and also work this out. So we get this times the other one, and then 9 times 1 times 1. And that is then equal to, if you work out this parenthesis and take the terms together, s to the power 4 minus 4 s squared plus 9. Now the solution of this Q is equal to s to the power of 4 minus 4 s squared plus 9 as 0 is given by this. So you get a fourth order polynomial equated to 0, and we need to use the formula for quadratic formulas actually, but then of course remembering that this is a fourth order system, so you will have 4 solutions. That's why we have s squared is equal to minus of this value plus or minus square root of this minus 4 squared minus 4 times the 1 here, that's the coefficient in front of the s to the power of 4, times also the 9 here is a constant, divided by 2 times the coefficient of this here in front of this s to the power of 4. If I work this out, you will get this, and if you work it out even more, you will get this, because that's just 20 inside of minus 20, so you will get j squared of 20. If you work it out even more, you will get 2 plus or minus j the square root of 5. This can be also written in the Euler representation, so you will get r times e to the power plus or minus j theta, where r is actually our length, so it is actually the square root of 2 plus the square root of 2 squared plus the square root of 5 squared together summed, and then the square root of that will be just 3 exactly, and the theta is the arctangent of the imaginary value divided by the real value will be then approximately 48 degrees. Now that means this will be then s squared will be then 3 times e to the power plus or minus j 48 degrees. Okay, now we have a nice expression for our solutions for our poles. So this is the 4 roots or 4 solutions for our q are then given by this. This is what we had, and this can be then also written in this form, so you can just take the square root of the left and the right hand side, but you know that it will be then plus or minus the square root of 3, and also the angle goes by 2, so you will divide it by 2 if you take the square root of it. Now you will now have 2 solutions for each, so the plus and also the minus. So for the plus you will get this, so s1, 2, and you will have s3, 4, and you will have with the minus sign, you have actually 2 directions. So s1 will be then the one with the square root of 3 and then the plus face. S2 will be then again the square root of 3, but then with the minus face of minus 29 degrees, or 24 degrees, I mean. Now in a similar form for that one, the exact same, but just we have minus the square root of 3. Exact same, nothing more. But we have 4 solutions. Okay, now let's collect them together and I'll look at it in a pictorial view, because you can now see the S1, this one, and S2 here is actually the same but having a negative angle. And S3 here is minus square root of 3, exact same angle, and that's actually shown here. And S4 is minus the square root of 3, having a negative angle, it's actually shown here. Okay, now using the 2 left half plane poles, so S3 and S4, we can form the Hurwitz polynomial DOS as follows. So we can say it is S minus S3 times S minus S4. Now let's see what we have as S3 and S4. We have this. Now if you work it out, the parentheses S squared, S times this times S, and this part times that part. It's actually all worked out here. Now you will now collect this. So you will get S squared plus this term times S, and this will be just square root of 3 times square root of 3 will be just 3, and you will see e to the power j 24 degrees times e to the power j minus 24 degrees, which is, of course, e to the power 0, which is just 1. So that goes to just actually 3. And this part is really similar to a cosine expression using Euler's formula. That's actually 2 times the cosine of 24 degrees. Then you will get d0, the polynomial, the polynomial we want, as s squared plus 3.16 s plus 3. This is actually the square root of 10, an exact form, just an approximation, that's 3.16. So the optimal overall transfer function now is then given by this expression, again, that formula. When we look again at the q, we have a 9. We look at the n, and also the polynomial we have this just determined and also evaluated at 0. So let's do that. 9, 1, 1 because that is the ns, and also evaluated at 0, it's still 1. We have a 3 here because if you just look at this one at s is equal to 0, just this last term, the constant 3, and 1 over that polynomial. Now if I now work it out, you will get 3 over s squared plus 3.16 s plus 3. Now you can see that the optimal transfer function is determined. You also see that the steady state error here for position, that's actually the latest discussion, is also 0, because when you do here s0 will be 3 over 3, just 1. Okay. Let's move on and then look also at the computation of the spectral factorization. So design of a quadratic optimal system requires the computation of that spectral factorization. The method 1 is hand calculations, we have just seen. So calculate all the roots of that Q for a given plant in this format. and group the left half plane roots, the poles, to form that polynomial which is called the Hurwitz polynomial, and calculate the optimal transfer function G optimum using this formula, of course with a weighting factor Q. Or you can use MATLAB. So for example, in our first example we had this Q. Now you can calculate the roots of this polynomial very straightforward. You can say Q is equal to this, so 1, 0, minus 4, 0, 9, because this is the fourth order coefficient. Third order coefficient, there is no third order, so that's actually a 0. You have also a second order coefficient, which is a minus 4. First order coefficient, there is no, so that will be also 0. There's also a zeroth order coefficient that will be 9. Now if I just call it Q and then say R is equal to the roots of that Q, I will have the following solution. And you can see these are the roots. We also have determinant now given in the rectangular form in the Cartesian domain with a real and imaginary value. Now we need to group the left half plane roots or the poles, which are these two, the first one. And that can be done also in the MATLAB by using DO poly and then taking R1 and 2 in this format. And that will generate this. You can see 1, 3.16, so 3.1623, that is of course exact, which is of course in exact form square root of 10, and also 3. That means actually the following, because we have 3 terms here. This is the second order term, the first order, and the zeroth order. That's actually what we also had from the hand calculations, which was s squared plus 3.16, of course, rounded off, s plus 3, and is exactly the same also here from the MATLAB. So looking just an example, that the hand calculation also the MATLAB will produce the exact same. Of course, this is in MATLAB much easier when you have a more complex Q value, so you can always do that in MATLAB when you want to bypass that tedious calculations. Okay, let's move on and see more that in general view. So if I now have this Q given by these products, so the Hurwitz polynomial and also its minus s version. Now the degree of this Hurwitz polynomial DOS and also DO minus s are the same. So the degree of DOS is half of the degree of that Q, what we get from the spectral factorization. So if the degree of Q is 4, just an example, then the degree of DO, so the Hurwitz polynomial, must be 2. So we can write it down in the general form as this one, B0 plus B1s plus B2s squared. Where it is required that BI are all positive or all negative. It can be also true, but we will just focus on all positive format. If one of the BI is 0, or positive or negative, when we of course select the positive it is negative, or when we select the negative it will be positive, then DO of S is not a Hurwitz polynomial. So that is also one of the conditions to make this Hurwitz. Now then we can write also for DO minus S the following, and then also simplify that in this format. Now the product of the Hurwitz polynomial with the s and Hurwitz polynomial with the minus s will be then this. So this part times this part is shown here. If you now work out the parentheses, you will get BO squared plus 2BO times B2 minus B1 squared parentheses times s squared plus B2 squared times s to the power 4. That's now the Q. Okay. Now let's look at an example again, the example 1, the Q with s to the power 4 minus 4s squared plus 9. That was our Q. Now in order to meet the Q in example 1, I require, looking at the coefficients, that the B2 squared is actually 1. Just this one. So you need to look at it actually in the reverse form, so this s to the power of 4 coefficient is 1 here in our example. That means b2 is just 1, the square root of 1. Of course, square root of minus of the square root of 1, but you cannot have a minus value, otherwise it's not Herbert. We just, of course, only choose the positive values. Another one is the b0 squared, which is the constant value, which is 9. That means the b0 is 3, square root of 9. Now, since we know the b2 and also the b0, we can calculate the b1 using this final form. So this one must be minus 4. Now, if you work it out and then substitute the values we have, we get the square root of 10, which is approximately 3.16. So this is exactly what we had also when we did it in another way, and we have our Herbert's polynomial. But we can also make it even more general for the procedure, not only for the 4th order, also for the 6th order, etc. So let's also look at that. So the 4th order polynomial for Q is given by this. So a0 plus a2 s squared plus a4 s to the power 4. This is our equation number 1. Then we can write the Herbert's polynomial for this case as a 2nd order general expression, and also for the minus s. Now let's then again multiply these two. This is then a general expression. Now what you see is the following. Now we will compare equation number 1 and 2, the terms. And we see directly b0 is equal to square root of a0, so the a's in the q and also the b's in the q here in the 2nd equation. In addition, you see b1 is, so b1 here, can be then rewritten in this form, so just looking at that. And a b2 is then, this one, b2 squared, is then equal to a4, so b2 is then square root of a4. So we have now 3 equations. Solutions can be found directly because once you know the b1, b0 and b2, you just substitute it in here, because a1 is also known from the q, which is what we have calculated. Then we can calculate also b1, so that is just done directly. So this is straightforward business. But for the 6th order or higher order polynomials for q, the calculation is a little bit different. So we have the 6th order here, a0 plus a2 s squared plus a4 s to the power 4 and a6 x to the power 6. Now then we can write again our Herbert's polynomial, but in this case with a 3rd order polynomial. So b1, so b0, b1, b2 and b3. And also for the minus s variant. Okay, then we'll multiply. So we multiply the dos and do minus s. Now, if you work it out, do the, let's say the parentheses correctly, you will get this final result. What do you see? Let's call this also equation number 4. We will compare now the terms in 3 and 4. I see the first one, which is easy. a0 must be b0 squared, or b0 must be the square root of a0. We also see that this 2 times b0 b2 minus b1 squared must be a2. Okay. We also see this b2 squared minus 2 times b1 b3 must be a4. And the final one we see minus b3 squared must be equal to a6, or b3 squared must be equal to minus a6. Now, we need to, of course, have positive numbers, so we can say this is it, but we will take only the positive value, so absolute value of that minus a6. We can calculate the a0, the b0 and b3 directly from the coefficient of the q in equation number 3. But these two are not that easy. So we can, of course, set an equation for b1 and also for b2, but it must be worked out and the solutions determined via an iterative process. Now we will now discuss that. How is that done? Now, iterative process of this for this expression. Now, step 1 is choose a value for b2, just a random value, and call that B2 of 0. So just actually the zeroth choice, so your first choice. And use this value of B2 to calculate then the B1 as given by this. So this is actually the next step for B1, using the initial choice for B2. Now, in step 2, use this B1 which you have determined from the initial choice of B2 and calculate again B2. So look actually at the new value of B2. Now, that is again done like that, using this formula. Now, if B2 of this calculation is equal to your initial choice, then the chosen B2 is a solution. But this is not really likely, so the probability of having this first time right is very, very small. But you could have a nice, let's say, guess, and if that is the case, then your B2 that you have chosen in the initial case is really a solution. Otherwise, you need to repeat this process until you have the B1 and B2s converging to a value which are the true solutions. Okay, we need to show this in an example, otherwise it's too confusing. So let's compute the spectral factorization for this polynomial, which is 16 minus 15s squared plus 21s to the power 4 minus 9s to the power 6. So calculate the spectral factorization of Q. That means we need to have these Hurwitz polynomials also. So let's also do that. So Hurwitz polynomial times its minus s form. And we have then this one and also the minus s. And this is our general form for a sixth order Q polynomial. Again, this, and I substitute this because we have also the minus s form, and we have this expression we just discussed. Now, comparing the terms in 1 and 2, what you see is this and this and this. We have discussed this also. This is the absolute sign of this minus a6. So we denote this as equation number 3 and 4 for the B1 and B2s. Okay, and this must be done via iterative solution. Now, step 1, determine the B0 and B3 directly. We can do that because that's all here. So let's do that. Just the square root of 16 because that's here and that's equal to 4. The other one, just absolute value, of course, it also must be here, of this minus 9. That must be then the square root of minus 9. Absolute value will be 3. That's done. So we have 2 of the 4 unknowns in our Hurwitz polynomial. Now substitute the values of B0 and B3 in equation number 3 and 4. So what we get, now B1 is this, because we know that also A2 is minus 15. You get this. And for the B2 you get this, so 2 times B1 times 3 plus 21, because 21 is that A4. Okay, now let's also write down this in a more simplified form. So 2 times 4 is 8, of course, and then this is the minus minus of a plus, and this will be 6 times B1 plus 21. Now we need to use these two equations also to determine the B1 and B2s using iterative process. So B1 and B2 using iterative process, that's step 3. We choose a value for B1, and I just call it, I just take 5, just random. You can also take 0. Of course not negative, always positive. And see what we get. Now, then we generate the following table. The table is very handy. So B2 is what we have chosen and B1 is what we get. So this is the 0th position, so actually step 0. This will be the first step, second step, etc. What you get is actually following. You just substitute this 5 in this expression. So you get 8 times 5 plus 15, and the square root of that will give you this result. So the square root of 55 will be then 7.416 approximately. This value now you will put in here. So 6 times this plus 25, and the square root of that will produce you 8.093. You will get now this, produces put it in here, that will produce now this. You will take now this value, put it in here in the B2 formula, and you will get this. Similarly, this one goes in here, so you actually do this, and then this value again in this form in the equation of where you have the B2, and just move on until you actually see that these are converging. So I actually see something's happening, because it's almost 9.2 and this is almost 8.7. Now it's something happening. This is not changing anymore that much, and it's also quite steady. And I see here now sort of a solution. So it could be that this is 9.2 and this is then 8.7 already, or 8.73. So this is a nice solution, or a nice place to stop, because you can move on, of course, up to 100, but that's not really the case. So I think this is accurate enough, and we can say B1 is 9.21 and B2 is 8.73, or a little bit accurate just as it is shown here. Then we can use our Hurwitz polynomial and then substitute the B0, B1, B2 and B3, and B1 and B2 determined using this iterative process. Okay, that's for this example number 2. Now let's also look at the selection of the weighting factors, the Q. So how do we do that? Now, an implementable overall transfer function to minimize the quadratic index. This is again what we have, and this is what we always do for the R, which is the step input. Now, spectral factorization, we have discussed this, and this is the formula we need according to this. Now, if I now take a large Q, that means there is a larger actuating signal, and the response is also faster. So response goes faster because I have more power in my system. But if I take a small, there will be also a small actuating signal, and there will be also a small response, so slow response. Of course, there is some limit here, so I can go up to some value with my Q. It really depends on the constraint U. So the procedure to select the weighting factor Q is as follows. So you actually choose just a random value for Q, of course positive, and carry out the design. Then you simulate your design of the overall system in step 1. If the process is slow, you can increase it a little bit of that Q, and then repeat design 1. Now, increasing Q will of course produce a fast response, but that will also increase the actuating signal, and the plant might be saturated. So you need to do this also iteratively, and then see where you can stop actually with your Q. Now let's also look at an example for the selection of the weighting factors of a third order system in this case. Now this is our plant given in also in the general form n over d, but then this is a third order system, 2 over s times s squared plus 0.25s plus 6.25. We need to design an optimal overall transfer function to minimize the following performance index given here. Now again, the reference input is a step, and there's also a constraint which says that the u must be smaller than or equal to 10 for all time larger than or equal to 0. But we don't know much about the q, so there's nothing given about the q. So we need to determine that. That's also one of the objectives of this example. So the step 1 is we just choose something. So let's say q, and determine the polynomial. The q is this, and the small the q, and the capital letter Q for the polynomial is then this one. We have our 9, 2, and 2 for our n. So we have everything, and this will be then our solution for the q, the capital letter Q for the polynomial. The polynomial in general for a sixth order q is shown here, and for the Hurwitz polynomial, of course, the third order general form is shown here. So again, we compare the results, the terms, and we have this. Now we can again start the procedure by calculating B0 and B3 directly using this. So this is just 6 and 1, so we take the absolute value of that minus 1 in the square root. Now you need to substitute those B0 and B3 in the equation of B1 and B2, and then use iterative process. So again, you see this here, A2 is actually here, and that is the minus 39.06. That's actually what you hear, but you have a minus sign also here, so you will get a plus. In the symbol form, you will get that minus 12.44 from that A4, which is actually shown here. Now you have two equations. Again, we need to do that iteratively. Okay, let's bring it together and then use the iterative process and then generate the table and choose, in this case, another value for B2. I just select 2 and generate the table. Now we just start with 2. We move up, so we just place this 2 in here and calculate B1. That's this 7.941. Use this 7.941 in here and you will get the B2 new value, so it is now 1.856. This actually means that this choice of 2 was pretty close to what I actually should have in the, let's say, the exact or the true solutions. Now I will now use this value in here and move on to calculate the B1. Now it will be then 7.832. Again, use this value and go in here, and it will be then 1 point. So I go a little bit down here, 1.796, and moving on in the same fashion. So what you see is it's sort of converging to some values for B1 and B2 also. So B1 is, yeah, sort of 7.75, and a B2 is 1.75. Again, this is what we had, and this is now what you get for B1 and B2. And then you get this polynomial. So 6 plus 1.75s plus 7.75s squared plus s cubed, because the B3 was 1. And that is now our Hurwitz polynomial. Okay, the optimal overall transfer function now is this. Now, if I now use the Q I have selected and also the rest of the values here, I will get this. And if I now work it out, I will get 6 over this expression. So if I now, for example, substitute here s is 0, the steady state error for position input will be 0 because the DC value of this one is 1. Okay. Now for this optimal overall transfer function, it is found that the actuating signal was smaller or equal to 3. So the maximum value was just 3 for all time larger than 0. So we may choose a larger value of Q. You might ask, how do I determine that U was much smaller or equal to 3? What you can do is you look actually at the closed loop transfer function of the system, and then do the inverse Laplace transform in MATLAB, or you do the step response and you see directly the transient and you see how large that is responding. That is one of the ways to do that, and that's also done, and that produces a 3 as a maximum value, and that means I'm way below that 10, so I can go up with the Q. Maybe I can make it, for the Q I can make it maybe 10 or maybe 15, but at some point it will, of course, have a problem with this constraint of U. Okay. Now let's also look at the specific topic, which is the ITAE optimal systems, which is our next condition or next topic. Now this is the integral of the time multiple multiplied by absolute error. The objective is minimize the integral of the time multiplied by absolute error. So for quadratic system G, the ITAE, or the integral of the absolute error, and the integral of the square of the error as a function of the damping ratio is shown actually below for this specific general transfer function. What you see is the following. This is the index, so how large that index is. This is that zeta for the second order system, very general. So we have a natural radian frequency of 1 here, and also the DC gain here is also 1 here. So very standard second order model. Now for the J4, so ITAE, you see this is going in this fashion. And for this case, you see that the change is not that much, and also for the J3 is that not that much. So you can select, depending on what you prefer for your damping ratio, the specific performance index. Okay, now we have several criteria to make the error zero. First one is the position. So we would like to have, for this optimal design, that we have a zero position error. Now, general transfer function for that is this. So this is the closed loop transfer function, y over r, and this is now the alpha 0, just the constant, over the polynomial in the denominator. Again, if I look at this, if I substitute for s as 0, I will get a alpha 0 over alpha 0 will be 1. So it is stable and it has no steady state error for step input. It will have, of course, a steady state error for other inputs like ramp or acceleration. The optimum coefficient of the denominator based on this criterion for step input are given in this table. And these are the polynomials you will need to use in the denominator of your system. So this is for the first order, for the second order, third, etc. So up to sixth order are shown here. It depends on omega n. So if omega n is changing, you can just add this here. This is just let's say a template format given in terms of omega n. Now you can also have the zero velocity error optimal systems. And again, general view, you can see now we have a s term here, and if I now look at this, it is the same denominator but the numerator is changed. And again, this is stable and it has no steady state error for ramp inputs also. The optimum coefficients for the denominator based on the ITAE criterion for ramp input, ramp is that linearly increasing input, is given by this. So we start actually at the second order up to sixth order. Also similar to the first table. But it is different, so we have different coefficients here. The final one is a zero acceleration error optimal system. Again, general format. Now we have a second order polynomial in the numerator. Again, it is stable and it has zero steady state error for acceleration. The coefficients for the denominator for this situation are then given here. So we start at the third order up to sixth order here, and again you see the values for each order. Okay, let's look at two different examples. Example number 4 first. So we have a plant given here, it's just second order, and we would like to have a zero position error system to minimize that criteria subject to an actuating signal which is then smaller or equal to 3 and due to a reference step input. Okay, solution, how do we work this out? Now, according to the table, the second order ITAE optimal overall transfer function is given by this. So we have just showing you the first and the second order is this. If I now use that, that means the denominator as optimal overall transfer function, and the numerator is omega n squared, because this was the alpha 0, so we have also the alpha 0 here. Now we have our optimal transfer function in general form. Only what we need to know is the omega n. Now the closed loop transfer function from the reference up to y is given by this. So r to y, that's actually given, actually r to u, I must say. So it is in this. Now we have then g optimum over g what we have given as a plant. Now just actuating signal u is then given by, this is then actually this, so if I work it out. Now if I now look at my actuated signal u, that will be this. Of course the r was a step input, so it's unit step, so 1 over s, and I have this expression for my u. Okay, that is now for this. And this is now the response if I do that in MATLAB. So just plotting the unit step response of this t. You can see that it is indeed going at the maximum value of 3 for this condition. And also decays to 0. So there will be then, in this case, no steady state error. So this is actually an error plot for the position. So maximum of this plot will occur at the origin, or at time is equal to 0, and it will be then 3. So we are at the edge. Okay, now what is an omega n done here for this case? Now the larger value is set is at t0 seconds, which is 3, and using initial value theorem, we get the following. We can say u max is equal to the limit of s approaching infinity, s times the u. We know u, and if I now work this out for this condition, I see that it will be then omega n squared. Now, that is 3, because we know that is 3 according to our plot. That means omega n itself then squared of 3. Thus, using the table and also the general formula we have determined, we can now substitute omega n here, which is then square root of 3, in this formula. So you will get 3 here, you will get square root of 3, and you get 3 here because that's the square of that square root of 3. And this is now our optimal transfer function for this case and also for this response. Now moving on, and we'll make it even more simplified, we'll get 3 over this expression. Okay, that's actually for this example for that specific error, but you can also look at the closed transfer function. This is the error. We know it has this value, and this is the closed transfer function. And this is now only the planned, which is our optimal system, specifically for the position. You can see it will have a final value of 1. And also I've shown some specifications like overshoot, settling time, and also the rise time. So rise time is 1.24 seconds. The overshoot is approximately 4.4%, and settling time is approximately 3.5 seconds for this situation. And this is the transfer function that will make this response. So we've actually determined an optimal transfer function using a given planned transfer function, using an actuating signal constraint, having also a reference input. Those are really important things. Now, let's also look at an example number 5, but then considering the exact same transfer function, but then zero velocity error constraint using the minimization of this ITAE criterion or index, subject to again the same actuated signal and also the input reference signal. So the solutions. So according to the table, we use of course a different table because it is zero velocity error. We have this. You see, you will get this in here, and in the numerator you will place actually this one without this s squared. But we cannot use that because it will be a violation of the pole zero excess inequality. So instead of this, we need to move on and take a higher order polynomial. That will be then this, and again you will take the exact same, let's say the denominator, but the numerator will, numerator will the same, but the denominator will stay actually as it is. So you actually only take this and you place it here. Okay, now the next step is then the following. You will use now this new G optimal expression and then also determine the closed transfer function going from R to output U. And output in this case is our actuating signal. Okay, this is the formula. G optimum over G. That's this. Now we have 1 over S times S plus 2. So if you work it out, you will get this. Now, thus the actuating signal U is then given by this. And 1 over S is because the R was a unit step input. or unit reference was unit step. So that will be then I lose this s here and also this s. That means actually I have this expression. Okay, what's the next step? Let's also plot this just in MATLAB and generate the step response for this t. So what I do is I just do step of this t will generate my unit step response for this specific case. I see the peak is not happening at the origin, but sometime later, which is then at 0.215. So it isn't always at the origin. And that's also 3. So specifically, exactly 3. So this is our u. And now let's also see how we can determine that time also. Now from simulations we can determine the omega n, which is 0.93 radians per second approximately. Now using that, and also in that ITAE optimal system we have selected as a third order, so then we can substitute our omega n here, cube it here, square there, and the rest also in the same manner. You will get this. Let me get back. And this is then our result, final one. Now, looking at the total picture again, this is the error. And this is our plot for just our optimal system we have designed, considering the zero velocity error for this criterion. You see again the final value is 1, but the overshoot is much higher, almost 39, and also the rise time is smaller in this case, and also the settling time is also much larger. Now this is happening because we have now put actually a unit step reference input and considering actually a velocity error criterion, which is a different thing. So it differs, but we put more emphasis in the zero velocity, not in the zero position. That's also the reason why you see these high differences between those two plots. And that's also what you need to be careful so that you don't over design your performance index. All right, this is for this video tutorial about the performance indices used in the controller system design. We have discussed how we can, let's say, read from a step response the criteria like the delay time, rise time, peak time, and overshoot and set state errors. Then we look at more carefully which one of these criteria could be more important. So we developed an analytical method for that and also showed that in specific situations and also discuss several examples to illustrate the concept in great detail. If you have any questions, comments about this tutorial about the performance indices, please let me know and I will try to answer them as soon as possible. Don't forget to like and share this video so that we can reach more people for this interesting topic. Thanks for your cooperation and see you next time in another interesting video. Keep in touch and take care.